Junction breakdown. When a sufficiently large reverse voltage is applied to a PN junction, the junction breaks down and conducts a very large current. Although the breakdown process is not inherently destructive, the maximum current must be limited by an external circuit to avoid excessive junction heating. Two important breakdown mechanisms are tunneling effect and avalanche multiplication. We consider the first mechanism briefly and then discuss the avalanche multiplication in detail, because avalanche breakdown imposes an upper limit on the reverse bias of most diodes. Avalanche breakdown also limits the collector voltage of a bipolar transistor and the drain voltage of a MOSFET. In addition, the avalanche multiplication mechanisms can generate microwave power as an impaired diode and to detect optical signals as in avalanche photodetectors. Now we discuss what is a tunneling effect. When high electric field is applied to a PN junction in the reverse direction, a valence electron can make transition from the valence band to the conduction band, as you have shown in this diagram. This process in which the electron penetrates through the energy band gap is called tunneling. The tunneling process occurs only if the electric field is very high. The typical field for silicon and gallium arsenide is about 10 to the power of 6 volts per centimeter or higher. To achieve such high electric field, the doping concentrations for both P and N regions must be quite high, that is greater than 5 into 10 power 17 per centimeter cube. The breakdown mechanisms for silicon and gallium arsenide junctions with breakdown voltages of less than about 4 Eg by Q, where Eg is the band gap, are the result of the tunneling effect. For junctions with breakdown voltages in excess of 6 Eg by Q, the breakdown mechanism is the result of avalanche multiplication. At voltages between 4 and 6 Eg by Q, the breakdown is due to the mixture of both avalanche and multiplication and tunneling. Now we discuss what is avalanche multiplication. The avalanche multiplication process is described over here in this diagram, that is the B diagram. The PN junction, such as a P plus N one-sided abrupt junction with doping concentration of Nd is equal to about 10 to the power of 17 per centimeter cube or less, is under reverse bias. This figure is nearly the same as we have seen earlier. A thermally generated electron in the depletion region gains kinetic energy, that is say by number 1, that gains enough kinetic energy and from the electric field. If the field is sufficiently high, the electron can gain enough kinetic energy that in collision with an atom, it can break the lattice bonds, creating an electron hole pair, that is 2 and 2 dash. These newly created electron and hole both acquire kinetic energy from the field and create additional electron hole pairs, that is 3 and 3 dash. These in turn continue the process, creating other electron hole pairs. This process is called the avalanche multiplication. To derive the breakdown condition, we assume that a current I is incident on the left hand side of the depletion region of width W, as you have shown in this figure over here. If the electric field in the depletion region is high enough to initiate the avalanche multiplication process, the electron current In will increase with distance through the depletion region to reach a value Mn, INO, where W and Mn, the multiplication factor, are defined as Mn is equal to In W and In 0. This is the multiplication factor given over here. Similarly, the whole current Ip increases from x is equal to 0 to x is equal to W. The total current I is equal to Ip plus In is constant at steady state. The incremental current at x is equal to the number of electron hole pairs generated per second in the distance dx. So we have, if we take the differential of din by q, this is equal to in by q alpha n dx plus ip by q alpha p dx, where dn by dx plus alpha p minus alpha n in is equal to alpha p I, where alpha n and alpha p are the electron and hole ionization rates respectively. If we use the simplified assumption that alpha n is equal to alpha p equal to alpha, then the solution can be written as INW minus INO divided by I. This is the integral of alpha dx, that is equal to I. So we have alpha dx is equal to 1 as we have shown over here. From both the breakdown conditions described about the field dependence of the ionization rates, we may calculate the critical field, that is the maximum electric field at breakdown at which avalanche process occurs. Using measured alpha n and alpha p, the critical field alpha EC are calculated for silicon and gallium arsenide one-sided abrupt junctions and as functions of the impurity concentrations of the substrate. Also indicated is the critical field for the tunneling effect. It is evident that the tunneling occurs only in the semiconductors having high doping concentrations. When the critical field is determined, we may calculate the breakdown voltages. As we have discussed previously, voltages of depletion region are determined from the depletion solution of the Poisson equation. So the breakdown voltage VB can be written as ECW by 2, that is equal to EC into epsilon S divided by 2Q NS to the power of minus 1. So for one side abrupt junction, the breakdown voltage VB is equal to 2 EC by W divided by 3, and this is equal to 4 EC to the power 3 by 2 divided by 3, 2 epsilon S by Q to the power of half A to the power of minus 1 by 2 for linearly graded junctions, where NB is the background doping of the lightly doped side. Epsilon S is the semiconductor permittivity and A is the impurity gradient. Since the critical field is slowly varying for the function of neither NB or A, the breakdown voltage as a first order approximation varies as NB to the power of minus 1 for abrupt junctions and as A to the power of minus half for linearly graded junctions. So we have shown in this figure that the calculated avalanche breakdown voltages for silicon and gallium arsenide functions as we have shown in this figure. The dashed dot line to the right of the high doping or high impurity gradients indicate the onset of the tunneling effect. Gallium arsenide has higher breakdown voltages than silicon for a given NB or A, mainly because of its large band gap. The larger the band gap, the larger the critical field must be for sufficient kinetic energy to be gained between collisions. The larger critical field in turn gives rise to higher breakdown voltage. So the space charge distribution for diffuse junction with the linear gradient near the surface and a constant doping inside the semiconductor, the breakdown voltage lies between two limiting cases of abrupt junction and linearly graded junctions considered previously, a large A and low NB. The breakdown voltage of the diffuse junctions is given by the abrupt junction results shown on the bottom line of this figure. Whereas for small a and high NB, VB is given by the linearly graded junction results indicated by parallel lines over here. Now we discuss the junction breakdown. The breakdown voltage of diffused junctions. The insert shows the space charge distribution over here. The layer, if the semiconductor layer W is smaller than Wm, as we have shown, the device will be punched through, that is the depletion layer will reach the N plus interface prior to the breakdown, increasing the reverse bias further and the device will break down. The critical field EC is essentially the same as that we have shown. Therefore, the breakdown voltage VB dash for the punch through diode is given by VB dash by VB is equal to shaded area in this figure which we have shown over here, divided by ECWM divided by 2. Punch through occurs when the doping concentrations NB become sufficiently low, as in P plus pi N plus or P plus V N plus diode, where pi stands for lightly doped P type and V stands for lightly doped N type semiconductor. The breakdown voltages for such diodes calculated are shown over here. For a given thickness, the breakdown voltage approaches a constant value as the doping increases. When the N type region reaches 20 micrometers, the punch through will occur first. So we can obtain VB dash by VB. This is equal to shaded area in the diagram which was shown over here in the inset of this, divided by ECW by 2. This is equal to W by Wm into 2 minus W by Wm bracket close. So VB dash can be written as VB into W by Wm into 2 minus W by Wm, this is nearly equal to about 449 volts. Another important consideration of breakdown voltage is the junction curvature effect. When a PN junction is formed by diffusion through a window in the insulating layer of a semiconductor, the impurity is diffused downwards and sideways. Hence, the junction has a plane or flat region with nearly cylindrical edges as we are shown over here. So, the junction has, if the diffusion mask contains sharp corners, the corner of the junction will acquire through the roughly spherical shape, and because of the spherical and cylindrical regions of the junction, they have high field intensity. They determine the avalanche breakdown voltage. The calculated results for silicon one-sided abrupt junction are shown. The solid lines represent the plane junctions considered previously. So we note that the junction radius Rj becomes smaller, the breakdown voltage decreases dramatically, especially for spherical junctions at low impurity concentrations. Thank you.